Hi there, welcome to the presentation on what it thinks is important. Robustness transfers through input gradients. My name is Alvin and I'm a PhD candidate from NTU Singapore. The key results of our work here is that it is possible to transfer adversarial robustness from one model to another model that has a totally different model architecture for the first time. First, what are adversarial examples? These are imperceptible perturbations that can be crafted in order to fool neural networks. While there are already several defenses that can train robust models, these methods usually rely on huge amount of labeled data or huge amount of computational resources to train them. Robustness transfer is one of the ways to reduce the cost of training a robust model. Current transfer methods transfer robustness through weights. In one example, where a robust model is trained on task A, what one can do is to freeze the weights of this robust model and fine-tune the final layers on another task, say B. While this method works in practice, there's an assumption that we want to keep the same model architecture from task A to task B. The question is, can we actually transfer robustness between models even though they have a different model architecture? To answer this question, let us look at what input gradients are. Some previous studies have shown that the input gradients of standard trained model and robust models look extremely different. In this example, with an input image on the left, if we feed it to a standard trained non-robust model to compute the loss value and backpropagate this loss value all the way to the input layer, we can see a very noisy input gradient. Whereas, in the case of robust model, we can see a much more meaningful input gradient. Input gradients can be loosely interpreted as what a particular model thinks is important in predicting its output. So in a way, robust models are actually relying on salient features that are actually also meaningful to the human eye as compared to a non-robust model on the top. And so the next question is, if we train a particular student model to have input gradients that looks very similar to that of a robust teacher model, will we be able to transfer robustness between these two models? In order to investigate this, we came up with a novel framework called input gradient adversarial matching. In adversarial matching, the student model is trained such that the input gradient will look more and more like that of a teacher model by fooling the discriminator model. Let's look at some results. In the case of an upwards transfer, where we transfer robustness from a relatively simple MNIST dataset to CIFAR-10 dataset, we can see that adversarial matching beats the baseline of fine-tuning the weights on the target dataset. We can also see that through adversarial matching, our model is able to have a very competitive robustness when compared to a very strong baseline that is being trained on 7 iterations of adversarial training. On another upwards task, where we transfer robustness from a CIFAR-10 model to a CIFAR-100 model, we can also see that adversarial matching beats the baseline of just fine-tuning the weights of the original model. In this case, we can also observe that when transferring the robustness through adversarial matching from a more closely related dataset, say for example from CIFAR-10 to CIFAR-100, we can see a better performance in terms of adversarial robustness. Next, we also look at downwards transfer, where robustness is being transferred from a more challenging Tiny-ImageNet dataset to CIFAR-10. In this case, we can see that the transfer robustness is still very competitive even under very strong attacks when compared to strong PGD trained baselines. One surprising result we see here is that even though the teacher model is being trained on a more challenging Tiny-ImageNet dataset, its clean accuracy and the adversarial robustness underperform its own student. One possible explanation to that is that, unlike the teacher model, 100% of the weights of the student model is being trained on the target task, which is why it is able to do much better on the final target task. Finally, when we look at the input gradients of our adversarially matched student models, we can see that they are very similar to those that are coming out from a very robust baseline, hinting that through input gradient adversarial matching, we are actually learning to see what is important in the image.